The Cartesian plane consists of the set of pairs of real numbers. The first component represents the signed distance in the horizontal direction, and the second component in the vertical direction. For example, the point with coordinates 2, -3 is the one which is 2 units in the positive horizontal direction and 3 units in the negative vertical direction. We often use the variables x and y to denote the horizontal and vertical components respectively, and when doing so, these variables are also called Cartesian coordinates. But these aren't the only coordinates we could use. In other words, there are more coordinate systems that could be used to describe points in the plane. A coordinate is, after all, just a parameter, or some number associated to a given point. In the case of Cartesian coordinates, the two parameters are, in some sense, the most obvious choices, namely, the signed distances either horizontally or vertically from the origin. But there's another distance that we could have used as a parameter as well, namely, the straight line distance, or the actual distance to the origin. This distance is some quantity too, or some parameter, which we'll denote by r. Although it's possible to make sense of negative values for r, we'll use the convention that r represents some non-negative number, or some actual distance. In other words, the number r is allowed to be any quantity in the closed interval from 0 to infinity. But a single choice of r is not enough information to represent a unique point in the plane. Indeed, there are many points in the plane that are a given distance from the origin. In fact, there is a circle of such points. As a result, we realize that if we're trying to devise a new coordinate system, with r as one of the coordinates, we'll need another coordinate too, a coordinate which can determine a specific point along a circle. One natural choice for such a coordinate is a rotation angle, say theta, which can describe how far along the circle our given point is. To normalize this choice of rotation, let's say that theta represents the angle of rotation in a counterclockwise fashion from the x-axis. By the time the rotation angle is 2 pi radians, we've already covered all of the rotation angles, so it's natural to allow theta to be a rotation angle in the half-open interval from 0 to 2 pi. This way, we'll avoid possible redundancies in theta. As a result, we now have two new coordinates, r and theta, which constitute a new coordinate system for describing points in the plane. Indeed, any point in the plane will be lying at a unique distance r from the origin and lying at a unique rotation angle from the x-axis. This new coordinate system, denoted by the variables r and theta, is often referred to as polar coordinates. At this point, then, we have two coordinate systems in the plane, namely Cartesian, which we knew from before, and this new polar coordinate system. It's natural to wonder whether they're related to one another by an explicit formula. Geometry and trigonometry provide an answer. Remember that r represents the straight line distance to the origin, which, in terms of Cartesian coordinates, is just the square root of the sums of the squares of x and y. In addition, the angle theta is just an angle in an appropriate right triangle, which, in terms of trigonometry, satisfies the relationship that tangent of theta equals y over x. On the other hand, the cosine of theta is the length of the adjacent leg over the hypotenuse, which, with our notation, is just x over r. And so, after solving for x, we obtain that x equals r cosine theta. Similarly, the sine of theta is the ratio of the opposite leg over the hypotenuse, which is y over r, and so y is given by r sine theta. These expressions of x and y in terms of r and theta suggest the following important interpretation of sine and cosine. Namely, if r is specialized to 1, that is, if our point belongs to the unit circle, then the Cartesian coordinates admit the descriptions x equals cosine theta and y equals sine theta. What this means is that cosine theta can be understood as the x-coordinate of the point on the unit circle with a rotation angle of theta, and sine theta is the y-coordinate of the point on the unit circle with the rotation angle of theta. This geometric understanding of sine and cosine has its advantages. For example, as we just noted, the point with Cartesian coordinates x equals cosine theta and y equals sine theta is just a point along the unit circle, which means that its distance from the origin is 1. In other words, 1 is equal to the square root of cosine squared plus sine squared. Squaring both sides of this relationship gives the ordinary Pythagorean identity of cosine squared plus sine squared equals 1. As another example, the point with the rotation angle theta is the same as the point with the rotation angle of theta plus 2 pi, because the addition of 2 pi just means that we have gone an extra time around the circle. As a result, we obtain the periodicity relations of cosine theta equals cosine theta plus 2 pi, and sine theta equals sine theta plus 2 pi.